Everybody else kind of knows how it might be stable.
Okay. Quickly coming up to Thanksgiving break. 4 weeks too late, but it's coming. I don't know why this TV is not on. But so the goal is for today, finish up homework 4, and then Friday we won't have class. There's a conference going on Friday, so yeah, just take a breath, and then we'll come back on Monday, build quiz number 4, and then work on project 4, like looking at launching things into space and de-spinning. It does have a Tesla in the project, and with all of the politics going on, I feel like we should rewrite it and not have the... Have you seen the latest news? Is that Elon Musk is going to become a government efficiency government official? Oh. Like, why is this happening? It feels like a bad dream, like something that the Simpsons would make fun of, but this is reality now. Anyway, so it does have a Tesla in the project of like de-spinning this Tesla in space, but we can quickly delete that image and then maybe de-spin Elon Musk, like actually launch him in the in the Tesla. Just get him out into space. Put him on Mars. He's been trying to get to Mars for a while. Let's just like send him out there. Leave him there. Yeah, he can go rule Mars. He can have a capitalist dystopian society out there. What were we doing again? Oh yeah, dynamics. Okay, so we got one more problem in homework 4, and the idea is like we have this sliding ladder kind of mechanism. It also comes up like in other things, like there are like control mechanisms where you might have these like 2 collars, something connecting to. It's not always like 90 degrees to each other. Like one is in one direction, another is in another direction. So as one side slides down, the other side slides out and away from it. Yeah. I don't know. I can't get it to work. Turn display off. Turn display on. Usually that's camera control. Not helpful. It doesn't seem to want to be on. There's a display mute. You can turn that off. Display off. Display on. Monitor off. Monitor on. It doesn't want to be on today. Oh wait, behind. It's weird. Behind us now, I'm on camera. I'm not recording. Well, I am recording on YouTube, but not the camera. Yeah, so I don't know what's going on with that TV. It just doesn't want to work today. It's already on Thanksgiving break. It's done. So it's gonna slide down the wall, and what our main goal is, like, as it's sliding, we want to know how fast it's moving as it moves down the wall. So first question is, like, what would cause a change in speed for this thing moving down the wall? Like, why would it? Is it going to move at a constant speed as it's sliding down? Or is it going to change? Is it going to move faster, move slower? What do you think? Yeah. Depends on angle. Yeah, so maybe there's some kind of constraint on the problem. All right, so we know this L equals 1 meter. Its initial angle is 0, and then we'll call it the final angle, or like 2 theta 1, theta 2. Call it that. So we're going to start off kind of like flat against the wall and start sliding down the wall. So something causes it to like start sliding, but initially it's kind of at rest. So if it's perfectly upright, it's going to be really unstable to start. So if there's even the slightest amount of initial angle, even if we said that it was like 0.00001 radians, then it'll start moving down. But we're just like assuming that it's kind of straight up, but something causes it to start moving down. And then, do we need we do have the mass, so we can write it down. So we got 0.5 kilogram on a rod coming down. All right, what do we want to do? So we want to know, as this thing moves from one position to another, how fast it's going. What kind of equations do you want to set up? Where do we want to start? Yeah. So initially we know it's not moving. We're moving like basically 0. So we're doing that. No, it's like a rigid body. Yeah. 1 meter long rod. Let's start trying to find position and velocity. Yeah. Got it. Something stopping it from going past that, or? So once actually, this is like a classic physics problem, like a sliding ladder. If it reaches 2/3 of its initial height, it loses contact with that vertical wall. So this is just a point before where it's at. Unstable. A little stuck. Not sure where to go. All right, big. So at least like big picture items. If you're looking for position and speed, it's always conservation of energy kind of problem. So looking at like what work was done, how fast am I going? That's always, it's always going to give you some connection between how fast something is moving and how much work was done to it. You can always like create equations of motion and then integrate those. But if you're just looking for like how fast is something going after something has happened, usually work energy forms the quickest way to get there. So you're not doing like integrations of differential equations. So it should give us something that relates position and speed, where position is the whole thing, like the angle, how far it's moved, all of that. So if we have a way to describe kinetic and potential energy, and here it's frictionless, so all we need is kinetic and potential. As we fill in the details, we should be able to get a relation between like how fast it's going versus what angle it's at. Make sense? Seems like it should work. It's driving me crazy. I don't know what happened to it. So our general form is just like all the kinetic, all the potential, plus whatever work was done to the, like if there's anything pulling mechanical energy out or putting it in somehow. So that would be like motors or friction or damping. All those would be those non-conservative forces. But that one, nothing's happening. So it's energy is conserved. T1 and V1. We'll get T2 and V2 overall. It's got to be one value there. And initially, no kinetic energy, so that's nice. So now we get into the question of like, what is kinetic energy for this like rod? Like what is, like how do we describe how much kinetic energy it has? Or we could start off with V, whichever one you want to do. What do you want to do first? Potential or kinetic? Wherever you want to start. It's fine. Yeah, kind of like different components, but they're all like scalar values. Rotational, spinning, energy, and translating. So they add up into one. So this one, what is that? W? Or T is kinetic energy. V is potential energy. And then W is work put into that mechanical system. It's either put in or taken. There's no like external work added. Like if there was a motor pushing on this thing, that would be work input into the system. Or if there was friction as it was sliding down, then you could send work taken out of the system and negative force friction on the system. Oh, nice. Start off free body back. Yes, that works. This was a good idea. Take this. Draw the free body diagram, right? Like what are the forces acting on it? And this is a nice way to identify like what forces are doing work on your system, at least if you're trying to use work energy. If you want to do equations of motion, then you can sum up the moments, sum up the forces, set all those equal to MA. So reaction forces never do any work because they're always constraining, they're always applying a force perpendicular to the motion. So that Ry dotted with the amount that it moves in the y direction is always 0. Same with Rx. Like Rx is never doing work in that direction. So the only thing doing work is like somehow that mg delta h. So the bigger, more the height, more I lift it up, the more I drop it down. So that's all like potential energy kind of work. So we could just start off with that, right? mgh1 equals T2 plus mgh2. At least we got somewhere, right? Starting to get some real numbers in there. Yeah.
Is height be like the center point of the rod, or where is the height?
Yeah, where is height taken from? That is a great question. How much potential energy does a rigid body have? Does it change if it's like, does something have more potential energy if it rotates versus flat? No? Why not? Just no? Just saying, like, just got a feeling about it. It's a good feeling.
You do it because of gravity, so
Okay.
Why do you do it from the center of gravity? It shouldn't be there.
So center of gravity is the potential energy like spot. Kind of makes sense, right? So like let's say we have like a barbell, you know, like the old style, like old school, the 1900s weightlifter, big round barbells. One of them is being held vertical, the other one's horizontal. Like, so this one has like, if we call this R and R, right? MGH plus R plus MGH minus R, or 2mgh. And I'm kind of simplifying it into just like 2 point masses, but it works the same way for like even big like other objects. Versus this one has the same both objects are at 2 mgh. So if we're just talking about like center of mass of the object, that is our like potential energy spot. Kind of makes sense, right? And that's where the main like force of gravity is kind of acting through anyway. Like if I take all the sum of where all the points of gravity are on all the little discrete points, overall it's one vector pointed straight down at the center of mass. So my h is always going to be describing like this height, right? Cool, that's good. So rigid body or point mass, we can just talk about like what is the center of mass? That's our potential energy for gravity. Now the exciting part, how much kinetic energy does it have? How do we describe its kinetic energy? Yep, yeah, so yeah, okay. So it's still 1/2 mv squared, but then plus some rotational term, right? So what's that rotational part? How much rotation? How much kinetic energy does something have that's like rotating?
Omega squared.
Yeah, yeah. It looks exactly the same. It's just now we have like I, the moment of inertia, times how fast it's rotating squared. And sometimes people talk about these as like components, but energy is energy. Like if you have a joule of energy, it doesn't have like components to it. It's just, that's just how much it is, because it's always a scalar value, like mass. Like if I have one component that's like my lunch mass and one component that's my like clothing mass, overall I just have like one mass. I'm just 180 pounds, and that's it. How I divide that up doesn't really matter. Cool. So we have all the stuff, right? MGH1 equals 1/2 mv2 squared plus 1/2 I omega squared plus mgh2. Done. Wrap it up. Send it home. Do we need anything else? Yeah. Okay, nice. Thank you. Yeah, the angular velocity, the velocity, H1, H2, like all of that. Maybe H1, H2 we could kind of figure out. Like we could roughly kind of figure out the trig and figure that something out. But somehow, like we're getting to this point of like, I need more constraints. Because right now I just wrote down 4 different variables. They have to be connected somehow, but I haven't defined any connection between them yet. So I need some kind of like kinematic constraints to say, if I'm moving this fast forward, I'm rotating this fast. If my height is this, then I'm at this, like this is my angle for that height. Some, right? Like we need some kind of kinematic description of the problem. Excellent intuition. Nice. So I guess H is kind of, that's like our first sort of thing. We can probably figure that one out. So if we know we're at a given angle theta, do we know what that y component of r is? Like how high it is? Yeah.
This one would just be 0.5 half the rod, right?
Yeah, okay. So at theta equals 0, r is 0I plus 1/2 j meters. Cool. So I just define like when that angle's right up against the wall, that is my position, and my height is that y component. How about as the angle starts increasing? What's that one going to be? Yeah. Yeah. Okay. If you know that acceleration is constant. Okay. Yeah. So if you know acceleration is constant and you can solve for what that constant is, here we have that translation and rotation. So you can solve, that would be like you would set up the equation of motion to sum up the forces y forces x and some of the moments. Yeah. And then there's, I think overall there's going to be like one term that says this is my acceleration. Use yeah, now we're
Yeah.
So it's
Okay. Yeah.
actually
There's a lot of like similar triangles.
Yeah.
The big one and then two little ones. Yeah. I don't know why it has to go down. Yeah, why is it gonna be less than 1.5? Yeah. Yeah. That makes sense. Yeah. Oh, it's that circle. Yeah. Okay. You're not like too far off. We are describing. It's gonna end up looking the center of math travels in a circle. Yeah. Even though we have two flat strings. Circle.
All right, do like some similar triangle, popping and dropping. So we got one big thing describing like theta 2 like that. And I can split it up into these little similar triangles. Similar as in same, all the ratios are all the same. So this is L over 2, that's L over 2. So that distance here, like our x position, is that L over 2 sine theta 2. And then the height, how high we want, is that L over 2 cosine theta 2 along that J. And this is, I always think this is kind of cool because what we just described is that the motion is going to travel in a semicircle, a little quarter arch, even though we have two flat sides confining one flat bar to move along them. The motion is a circle. Not impressed. Seen this all before. Circles, you and your circles. Take your pie and get out of here. H1, H2, L over 2, cosine pi over 6. Looking good. It's a lot of things that we just identified. We know H1, we know H2. Now V2 and rotation rate. What's the connection between how fast it rotates and how fast it moves? Yeah. That would be if it's like rolling. Yeah. So when we have like if we're like rolling without slipping, then we have V equals omega R. and it's due to the constraint that this point and this point have to be the same speed, like where the wheel touches the ground and the ground are moving at the same speed. Ground 0, so overall we have to rotate around it at omega r. But here we have a little different constraint, and we already wrote up like this. This is actually describing like a constraint on that center of mass, at least if we leave it in terms of theta, because theta and its position, like x and y, have to be this equation, that for any angle that is the position of the center of mass. So I could say the position is always L over 2 sine theta 2 plus cosine theta 2. Or sorry, I don't know why I wrote the 2. So I do have like a constraint on center of mass and theta. So if I take a derivative, then I should get a constraint on center of mass, velocity, and theta, change in theta, the omega. So what does that look like? The velocity vg. I take one derivative of rg. G is the center of mass. Yeah, there's like L over 2 times both of them. Okay. Yeah. No. Yeah. Yeah, so it ends up being a unit vector. This L that is L over 2. Does this look good? L over 2 cosine minus sine. Nothing missing. We didn't forget the chain rule or anything. Chain rule. Don't forget the chain rule. Yeah. There's a theta dot, like that omega, the thing that we were like, because is it up here? Where is it? Yeah, we were trying to figure out like omega. And when I take, really what I did there was this equals drg d theta, which is good. That, like, I do need that derivative, but I have to multiply that by d theta dt. So then there's also an omega times that. change in the unit vector. This is nice because it's already split up into a unit vector and a magnitude. This is describing direction. And this is speed. So Vg squared is L over 2 omega squared. Or if I want to solve for like Vg, like how fast it's moving, or which one do I want to solve for? Angular velocity. All right, so we'll leave it in angular velocity. So mg L over 2 equals 1/2 m times L over 2 omega squared plus 1/2 I omega squared plus mg L over 2 cosine theta. Cosine? No, yeah, cosine theta. 2. So now we're in like much better solving, because the only thing missing is omega at this point. We have one equation, one unknown, instead of one equation, 4 unknowns. And the way we got there was we recognized, like, all right, we need some kind of constraints on our motion, and we know that the constraints exist, so let's look at the kinematics that were involved. General problem solving process. And oh, and even I, we can, it's always a table lookup value, right?
1/12 ml squared.
Yeah, nice. ml squared over 12. So m shows up everywhere. It doesn't matter how heavy it is. And anything else we can cancel out? And let's get rid of these 2's. And then L squared, so 1/4 plus 1/12. Oh my god. 3/12, 4/12, 1/3. 1/3. Now we've got a way to say, like, oh yeah.
With the
That one is not constant. We're solving for like at a given angle, this will be the rotational speed, like how fast it's rotating. But both theta and omega are a function of time. Like both of them are changing. It's just when we use work energy like this, it's giving us a result that's independent of time, that theta and omega are always some function of each other, or position and velocity. But in general, it's always like something describing where you are and how fast you're going. It's always work energy. So I think we're in good shape, right? 3GL, 1 minus cosine theta 2, all over, oh, I don't even need that top L, 3G over L. Unless I did the math. I mean, it's possible. I didn't do it. I'm just kind of rushing through it. Take the square root. We're in there. Yeah. It'll always be radians per second for rotation, and in general, like position, like if we're talking about like kinematics, position should always be in radians, and then rotation's always radians per second. It's kind of like the unspoken SI unit is always radians. And even if you use like foot pounds and inches, or foot pounds and horsepower, whatever you want to use, but always use radians so the units work out, because it's got to be a length per time, or radians per second. Cool. Done with homework 4. Yeah. So that one would be, like, usually I write it as a theta dot.
So if that's not a constant, like how do you want to not like everything is derivative of r? So how do you want to not be changing
So like when I went from here to here, what I did was replace this d theta dt with omega, and said that my definition for rotation rate is theta dot, so I'll write it in that omega. Because it, like, omega is not part of, I don't need rotation rate to describe position, because position is just based on the length and the angle. But when I take a derivative of position, now the velocity is a function of the angle, the length, and how fast it rotates. Yep. Cool, thanks. And then no class Friday, and we'll be back Monday, work on quiz number 4. Thanks a lot, have a good weekend. Thanks.